In this video, we're going to use bond and energies to calculate reaction enthalpy. We're going to use the combustion of ethanol as an example. So we have ethanol plus oxygen forming carbon dioxide and water vapor. We're going to start by drawing the Lewis structures for each of our compounds. I'm going to represent each bond with a different color so that we can later sort the types of bonds present. For any molecule with a coefficient of more than 1, I'm going to draw it more than one time, as we're going to be counting the number and type of each bond present in the reaction. The bonds that are present in our reactants will break. This is going to require an input of energy. The bonds that are present in our products will form. This will involve a release of energy. We're now going to count up how many of each type of bond are present. So we have 5 carbon-hydrogen single bonds, 1 carbon-carbon single bond, 1 carbon-oxygen single bond, and 1 oxygen-hydrogen single bond present in our reactant, ethanol, and then in the oxygen molecules we have 3 oxygen double bonds. In our products, we have 4 carbon-oxygen double bonds and 6 oxygen-hydrogen single bonds. We can use this bond energy chart to determine the energy of each bond we've just listed. So each carbon-hydrogen bond has 413 kilojoules. Each carbon-carbon single bond has 347 kilojoules. Each carbon-oxygen single bond has 358. An oxygen-hydrogen bond has 467 kilojoules, and an oxygen double bond has 498 kilojoules. Our carbon dioxide bond is 799 each, and oxygen-hydrogen is 467. So we can now multiply by the number of each bond that we have to get the energy held within that type of bond. We're now going to add together the energy of our bonds in the reactants. These are the bonds that are broken. We get 4,731 kilojoules, and the bonds formed, the total energy is 5,998. So if we represent this on a potential energy diagram, we can draw our reaction progress. So reactants form products. This is combustion, so it's exothermic. Products will have less potential energy. The energy required to break our bonds is going to be added because it requires energy to break bonds. So that's 4,731 kilojoules. The energy to form new bonds, that energy is released. And so we release 5,998 kilojoules. We can look at the difference in these two amounts of energy, and that will give us the reaction enthalpy. We can write this as an equation by saying the reaction enthalpy is equal to the sum of the energy of the bonds that are broken minus the sum of the energy of the bonds that are formed. So we can substitute our numbers in now. So 4,731 kilojoules minus 5,998 kilojoules, and we get a reaction enthalpy of negative 1,267 kilojoules. We can compare this to the reaction enthalpy calculated using Hess's law, and we see that with Hess's law, the reaction enthalpy is negative 1,235 kilojoules, so a little bit different. And this is because bond energies are averages of all measured bond energies in all different types of molecules and environments. So when we have a specific molecule that we're using, the energy may vary within that molecule itself. So bond energies are a good estimate, but not necessarily as accurate.